So basically, we are going to classify the amplitude modulator types based on how it is generated. So here we have classified first into linear and nonlinear type. So this is based on the operating range. So between the input and the output characteristics. So let's say if the device is operated in the linear range, the input output characteristics of the device are linear. And if it is operated in the nonlinear range, the device is made to work in its nonlinear operating device characteristic. So in such case, we have classified the modulators as switching modulators and transistor modulators when it is in the linear operating range. And if it is operated in the nonlinear range, we have a square law modulator, balance modulator, and product modulator. So all these are different types in the nonlinear category, and switching and transistor modulator comes under linear category. So we'll study one by one. We will take any one example for both the cases. And also based on another grouping is done based on the power level. So whether it is low level or high level. So when the generated AM wave is at a lower power level, it is low level amplitude modulators, and high level when the generated AM wave is at a higher power level. So we'll study one by one. So what are low level modulators? So the generation takes place at a lower power level. So based on the power level, we classify low level and high level. Modulation takes place prior to the output element. So before the output, when you see the block diagram, we are going to see that the low power modulators, it is going to take place before the output. Linear amplifiers are preferred here. So we will study what is linear amplifiers when the device is made to work in the linear range. And advantages here, less modulating power will be required. As the name indicates, it is a low power level modulator. And disadvantages, it is extremely inefficient due to the use of linear amplifiers. So generally, linear amplifiers will require less power level. So there are some disadvantages when we use linear amplifiers. So we'll study in detail. So heavy filtering will be required. So we'll see the drawbacks of linear amplifiers when we go to square law modulator. And high level modulators, the generation takes place at higher power level, and the modulation takes place at the output element. So when you see the block diagram of a transmitter, the high level modulators, generally the modulating signal is getting generated at near the output. Whereas in low level, it takes place prior, before the output generation, before the output, maybe nearer the antenna end, the modulation takes place at a high level, and before that, low level modulators work. Class C amplifiers are generally preferred. So Class C amplifiers, we know that generally it offers more efficiency. Class C amplifiers, and it is used for tuned operation. Class C amplifiers are preferred for high level modulators. Advantages here, it is extremely efficient due to the use of Class C amplifiers. Class C because it provides good efficiency. Disadvantages, high modulating power will be generally required. So what is a linear modulator? So the devices are operated in the linear range of its transfer characteristics. The relation between the amplitude of the modulating signal and the resulting depth of modulation is linear. So the input-output characteristics are linear, as well as the amplitude of the modulating signal and the modulation index. So they are having a linear relationship. So these are the two types, switching and transistor modulator. So what is called nonlinear modulator? So devices used in this modulation are operated in the nonlinear region of its characteristics, and it uses the nonlinear property of the diode, BJT, and FET. So all these are the devices which are used, and they are made to work in its nonlinear characteristics range. Simple diode can be used as a nonlinear modulator here. Undesired frequency terms are filtered using the bandpass filter. So when you see the block diagram, you will understand the final output will be given to a bandpass filter, where the second harmonics or the high level undesired frequency terms will be filtered. And these are the different types. We have square law modulator, balance modulator, and product modulator. So all these types of modulators will use either of these devices. We can use a diode, BJT, or a FET. So this is so we start with nonlinear modulators. So the first example is square law modulator. The modulating signal and the carrier signals be denoted as Vm of t and Vc of t respectively. So we are taking the instantaneous value of the message signal and the carrier signal. These two signals are applied as inputs to the summer. So here we are going to add both these signals and the output is going to be V1 of t. So V1 of t will be the sum of Vm of t plus Vc of t. So this is given as input to the square law device. So we are going to take the square law device as a diode, so which is going to work in its nonlinear operating characteristics. So the output of the diode is going to be V2 of t, which is given as input to the band pass filter. So here band pass filter, we are going to use a LC tune circuit. So this LC tune circuit is going to tune only the frequencies which are required. So only it is going to take the bandwidth of twice FM. So which is necessary for the AM generation. So we know that the cutoff frequencies, the sideband frequencies FC plus FM, FC minus FM, and the carrier frequency FC. So our signal should lie within that frequency spectrum. So this bandpass filter is tuned to work within that range. And V naught of t will be the final output, which is our generated AM signal. So these two signals are applied as input to the summer block. This block produces an output, which is the addition of the modulating and the carrier signal. So we'll see the detailed circuit. So now this is the circuit diagram. So here again we have two signals, modulating signal and the carrier signal. So the output of the addition of modulating and the carrier signal is V1 of t, so which is given as input to the nonlinear device, and V2 of t is the output of the nonlinear device, which is given as input to the filter. So this tuned circuit is a filter. So output is V0 of t, which is after filtering. So tuned circuit tuned to FC, acting as a bandpass filter. So we are going to take the nonlinear property of the diode and we are going to feed V1 of t. And based on the nonlinear property of the diode, we are going to apply an equation and we are going to obtain V2 of t. Then pass it on to the filter, bandpass filter, and get filtered the undesired components. So we can either use single or double tuning to get better filtering. Okay. So now we are going to do the calculation. Nonlinear device is V1 of t. So V1 of t is going to be the addition of the message signal and the carrier signal. So now we are going to add Vm cos omega mt plus Vc cos omega ct, which is the message and the carrier signal. Now, for the nonlinear device, the input-output relation is given as. So this is the voltage relation for the nonlinear device. So here we are going to take A and B are the constants. So A V1 of t. V1 of t is the applied input plus B into V1 square of t. So we are going to apply V1 of t in this equation. We are going to substitute for V1 of t. So here Vm cos omega mt plus Vc cos omega ct. So this entire equation we are going to substitute inside A and B. And second term we are going to take the square. So this is A plus B whole square form. So we are going to just expand. So the first term it is as it is, A into Vm cos omega mt plus A into Vc cos omega ct plus, so this is first term square plus second term square plus 2ab. So that is 2 Vm Vc cos omega mt cos omega ct. So this B is again taken inside. So this is just expanded. So you can observe here. So this square term. So this square term, all the second harmonics will be filtered, as well as the message cos omega mt term also will be filtered. So we are going to be left with cos omega ct and this term. So if you expand, what will be this term? Cos omega mt cos omega ct. What will be this term? Using trigonometric identity, if you expand cos omega mt and cos omega ct, cos of a minus b plus cos a plus b. So this term will be, here we'll have two terms, which is our upper and the lower side bands. Okay. So after bandpass filter, what will be the final terms? So we know that the bandpass filter is going to take upper and lower side bands plus the carrier component. So this, where is the carrier component here? Vc cos omega ct. This is the carrier component. And remaining two terms we are going to obtain from this term, cos omega m and cos omega ct. Okay. So all the other terms will be filtered by the bandpass filter. So now this V2 of t is going to be passed to a filter. So and the output is V0 of t. So we are going to take V0 of t. So this LC circuit acts as a bandpass filter and is tuned to the frequency of FC, and its bandwidth is equal to twice of FM. So we know that bandwidth is twice of FM. So this is our bandwidth between the upper and the lower cutoff frequencies. So therefore it allows only the carrier component and the sidebands. So we are going to take from the final output the carrier component plus the two sidebands. So here we are going to have 2b. So this, if you expand, this 1 by 2 and this 2 will be cancelled. After the trigonometric identity expanding, this 1 by 2 and 2 will be cancelled. So finally this is the output equation. So which is of the standard form. So what are the drawbacks? So here heavy filtering is required to remove the unwanted terms present in the output of the modulator. So we know that all these second order terms are going to be filtered by the filter, bandpass filter. So heavy filtering will be required. The power level where it is operated is very low. So nonlinear modulators are low level modulators. Hence a substantial linear amplification is necessary to bring the power up to the desired level. So that's why we move to linear amplifiers. So we'll study about linear amplifiers. So under this category is the switching modulator. Okay. So here again we are going to use the same device, that is a diode. We are going to use the same diode. So and the similar block diagram. So only it's the same similar block diagram, and the only difference here is the diode is going to operate in the linear range, linear VI, the input output operating range. That is V1 of t and V2 of t are going to have a linear relationship for the diode. This a simple diode can be used as an AM switching modulator. Consider the diode is ideal and the carrier is stronger than the message signal. So when the diode is forward biased, the positive half cycle of this carrier C of t will be greater than 0. And when it is reverse biased, negative half cycle of the carrier will be less than 0. So basically it is going to act as a switch. So it is going to act as a switch. So we are going to have high and low, okay, or positive, negative. Okay. So based on that, we are going to multiply a rectangular pulse with this V1 of t. So when this V1 of t is going to be multiplied with a rectangular pulse, so this diode operation is going to be satisfied. It is going to work as a switch. So when we are going to multiply this V1 of t with a pulse operation, and from that we are going to obtain the V2 of t. And again, this is going to be passed to a filter. Finally, we get the output after the filtering based on the bandwidth of the filter. Now this is the linear. This graph is showing a linear relationship between V1 and V2, between the input of the device and the output of the device, since switching modulator is a linear amplifier. So the transfer characteristic of the diode is approximate by a piecewise linear time varying relationship. So you can see a linear slope. So the input voltage is given as V1. V1 is going to be sum of the message and the carrier signal. Here V2 of t is, this is the characteristic of V2 of t. So V2 of t will be equal to V1 of t when C of t will be greater than 0. So that is during the positive half, it is going to be the same signal. It is going to be positive, and 0 when C of t is less than 0. Though when the carrier is positive, and what will happen when the carrier is negative. So it is going to behave as a pulse. Okay. So that's why we are going to take the pulse. So we are going to multiply V2 of t as V1 of t into Gp of t. So this Gp of t is a periodic pulse stream. So it's a kind of rectangular pulse whose period is 1 by Fc, 1 by the carrier frequency. Now we are going to represent Gp of t, the rectangular pulse, using its Fourier series. So this is the Fourier series of Gp of t. 1 by 2 plus 2 by pi summation n equal to 1 to infinite minus 1 whole power n minus 1 by 2n minus 1 cos 2 pi fct 2n minus 1. So now this again we are going to take this n equal to 1, 2, etc. inside. So we are going to expand this equation. So we are going to have the first two terms. So that is n equal to 1 and n equal to 2. So this Fourier series will be keep on going. So the n equal to 1 and n equal to 2 terms. So we are going to stop here, Gp of t. And this one we are going to multiply with this third equation. So ultimately we want V2 of t as summation of the message and the carrier plus the pulse. So after we multiply and filtering. So after you multiply, so we are going to have multiple terms. Okay, so like a square law modulator, we are going to expand it, and then after that we are going to pass it to a filter. So after filtering, so this is the final term that we obtain. So V naught of t is Vc by 2 cos omega ct plus into 1 plus 4 by pi Vc m of t. So here we have not expanded the message signal for simplicity. So here the message signal, if you substitute, we will have two components, cos omega c and cos omega m. So and we will get the two components, upper and the lower sidebands, if you substitute the message signal here, and then multiply and expand, we are going to get the upper and the lower side frequencies. So this factor, so 4 by pi Vc is denoted as K, which is the amplitude sensitivity.